So what is recurrence for running time of this algorithm? If both A and B are n by n matrices, what is recurrence for running time of this algorithm? Is that correct? Same thing we discussed, no? Okay. Recursive divide and conquer algorithm for square matrix multiplication. And we learned that this algorithm runs in theta of n cube time. Now later we understood that if instead of 8, if there is 7, running time will be improved. By which case 1, it becomes which is approximately n power 2.81. Is that okay? Okay. Now we'll see how to do this. That means number of sub-problems we are solving, each of size n by 2 is only 7, not 8. That's what Strassen has done. So in order to find product of two matrices, two n by n matrices A and B, whose result is C, he calculated some different matrices. Here S12, S10, similarly P12, P7. These are different matrices he calculated based on values of what? This. After A is divided into 4 parts, we have got like this, no? B also we have got 4 parts, B11, B12, B21, B22. With the help of A11, A22, A21, A12, like that. And with the help of these two matrices, these 8 components, he calculated this is 10 different matrices here, S12, S10. What is S1? B12 minus B22. We know what is B12. What is B22? All those things are clear to us. So easily we can calculate this. Now tell me, what is the time we require to calculate this? S1. What is the time we require to calculate S1? What is the time we require to calculate S1?
Square time.
Exactly, sir. It is B12 is one matrix minus B22. What is the order of this? So this is nothing but same as addition, no? Same as addition. So how many entries we need to calculate? How many entries we need to calculate? See, one entry here I need to add subtract. From this we need to subtract this. Similarly, next entry we need to subtract. Like this, how many entries we need to subtract? How many entries are there?
N entries.
No. B1. What is order of B1?
Number of elements in the matrix.
How many are there, sir?
By 4, sir.
What is order of B12?
N by 2.
N by 2. Then how many entries this matrix contains? If it has 5 rows and 6 columns, total how many entries are there in that? 5 into 6.
30, yeah.
Like this, how many entries are there in this B12 matrix? N by 2 whole square. Is that correct? Similarly, how many entries are there in B22 matrix? N by 2 whole square. That means we subtract one from the other. Like that, how many times we need to do? How many times we need to do? N by 2 whole square times. Is that correct? Is that correct? How many subtractions we need to do in this case? Both are 2 by 2 in order to find this.
Four subtractions.
That 4 is nothing but number of rows and number of columns, no, times number of columns, no. The answer is 2 minus 1, 3 minus 0, 4 minus 2, 5 minus 1. Is that okay? Is that okay? So this is 1, 2, 3, 4. 4 operations we are performing. What is 4 here? 2 into 2. This 2 into 2 is 4. Similarly, how many operations we perform in this case in order to calculate S1? How many?
N by 2 into n square by 4.
N square by 4. Thank you, sir. N square by 4. Similarly, S2. S2.
Yes, there also it should be same. It is same n square by 4 in all the cases.
Each one n square by 4. So these are some sum or difference matrices. Sum and difference both are same, no, order of n square time it takes, n square by 4, n square. Now, what is the time it takes to calculate A11 into S1? It is A11 into what is S1? B12 minus B22, which is same as A11 B12 minus A11 B22. How much time is required? How much time is required? To calculate this, how much time is required? What is the amount of time that is required to calculate that? Or we don't even require this. We don't even require this. Why? Because just a second. Okay. So what is the time? This is A11 into S1. S1 we have already calculated, no? S1 directly we can use this value, no? Why to again do that? S1 is here. Now this is it a multiplication or not? What is the size of this? What is size of this? Is that correct? Is that correct? Then in order to multiply two n by n matrices, time required, if we consider it as T of n, what is time required to multiply two n by 2 by n by 2 matrices? What is time required to calculate P1? See, in order to find the product of two square matrices of order n, time required is T of n. What is the time required to find the product of two n by 2 matrices, two square matrices of order n by 2? I repeat.
T of n by 2, sir.
T of n by 2, no? Is it clear? If both are n by n, time required is T of n. Here it is n by 2 by n by 2, so T of n by 2. What about this? S2 is n by 2 by n by 2. B22 also is n by 2 by n by 2. Here also what is the time required? T of n by 2. Here also what is the time required? T of n by 2. Like this, here also T of n by 2. T of n by 2. Is that okay? Again, we need to calculate finally C11 to C1. In order to calculate C11, what is the order of P1? What is finally order of P1? What is order of P1? Is it clear why it is n by 2 by n by 2? Number of rows in P1 is n by 2. Number of columns is n by 2. Is that clear? Why it is n by 2? Is that clear? Why order of P1 is n by 2?
Yes, sir. Clear. Yeah.
Why? Because here this is these two matrices we are multiplying. Order becomes this number of rows in first matrix, number of columns in second matrix, both are n by 2. Similarly, each of these matrices, no, they have order n by 2, n by 2. Now, P5, what is the order of P5? P1 to P1 to P7, what is their order? Order is that okay? N by 2? Is that okay? So now we need to, this is n by 2 by n by 2, n by 2, n by 2. So what is that we need to do here? What is that we need to do here? How many additions or subtractions we need to perform here? 3. Each addition, how much time it requires? N by 2 whole square. Is that correct? Is that correct? Is that correct?
Yes, sir.
Here also addition, this is n by 2 matrix, n by 2 matrix. It requires n by 2 whole square. Here it requires again n by 2 whole square. Here it requires 3 times n by 2 whole square. Now tell me what is the total amount of work we are doing in this algorithm? What is the total amount of work we are doing in this algorithm? T of n equals to this 10 matrices we need to calculate, no? What is the time for all these 10? 10 times n by 2 whole square, can we write? Is that correct? Is that correct?
Yes, sir.
What is the time for these 7 matrices? 7 times T of n by 2. Is that correct? What is time for these 4 matrices? 3, 4, 5, 8. 8 times n by 2 whole square. Is that correct? Now what is T of n? On
70 n by 2 plus 18 n by 2 square.
Thank you, sir. Okay, 7 times T of n by 2 plus 18 n by 2 whole square. Now tell me what is that? Okay, no, this is what is the name given to this method? Who has given this? Who has given this?
Recursive square.
This is Volcker Strassen. This is also recursive matrix multiplication only, but here they reduce the number of multiplications required subproblems of size n by 2 from 8 to 7, and that method was given by Volcker Strassen, and it is popularly known as Strassen's matrix multiplication method. Strassen's matrix multiplication method. So this is the reconciliation, and T of 1 is 1. Is that okay? Now what does 18 denote here? What does 18 denote here? And what does this 7 denote? What does 18 denote?
Number of
What does
7
denote?
denotes number of subproblems 7.
Yes, sir. Thank you. What does 18 denote, sir?
It is coefficient of f of n.
That is okay. With respect to this algorithm.
Okay.
Okay.
Constant.
Any
No.
better answer?
Number of
It's
editions.
combining the results and
Ah.
dividing also same.
So that is number of additions or subtractions of size n by 2 we are performing in this algorithm to arrive at solution. What is this? Number of additions / subtractions of size n by 2 that we are performing in this algorithm in order to find product of A and B. Is that correct? That means what is that Strassen has done? What is that in our old earlier algorithm, our divide and conquer algorithm, what was reconciliation? We had something like this, no? Our divide and conquer algorithm, general algorithm, we had 18 times T of n by 2 plus 4 into n by 2 whole square, no? We had like this. Now, what is the difference between Strassen's method and our general method? That means what Strassen has done is he reduced the number of multiplications from 8 to 7, but increased the number of additions from 4 to 18. 4 to 18. Correct? No, this is increment. This is more, no? But this is less. That means in order to reduce one multiplication, he has increased the number of additions and subtractions he is performing in the algorithm. But fortunately, because additions and subtractions, they are less costly, okay, no, compared with the multiplication, that's why he was able to get overall gain. So by first case of master theorem, it becomes T of n is theta of n power log 7 base 2, which is approximately n power 2.81. Is that okay? So what is that he has done? Reduce the number of multiplications from 8 to 7 with at the cost of additions. Still he was able to get better algorithm. It's a first breakthrough. Okay. After that, there are algorithm Cooper-Smith, Vinograd, all other algorithms are there. Okay, we are not going to discuss those things. Is it clear? Now, what is the question that comes to our mind? Okay, whatever we discuss, it is for square matrices. N is of the form 2 power k. If n is not of the form 2 power k, then what is that we do? If n is not of the form 2 power k, then what is that we do? For example, 3 by 3 matrix is given. How to multiply it? By applying Strassen's method. How to multiply it? By applying Strassen's method. 3 by 3 matrix is given. So what is that? No, this 3 by 3 matrix, 1 0 row, you add 0 column and 0 row. Then it becomes 4 by 4, no? No, same procedure we follow. Whether value changes? In the final answer, only this part we consider. Is that okay? If a size is, say, 13, how to multiply? How many 0 rows we need to add here? Given two matrices, they have order 13.
3 rows and 3 columns.
Because it is between 16 and 8. That means 2 power k minus 1 and 2 power k. Correct, no? 2 power k minus 1 k. So that means we will make it size 2 power k by adding sufficient number of 0 rows and 0 columns. That's all. Okay. So finally, what is a reconciliation means like this. Whether 18 is there or not, simply if someone gives 7 times T of n by 2 plus constant into n square, is it correct or not? Sometimes if it is written like this, T of n is 7 times T of n by 2 plus n square. Is this correct or not? Is that correct or not?
Right, sir.
Whether it is there or not, it doesn't matter. Some constant into n square. Is that correct or not? 7 times T of n by 2 plus theta of n square. Is that correct or not? All are correct. Once we know what is happening, after that we can write our own reconciliations. Or somebody gives reconciliations, we can verify whether it is correct reconciliation or not. Okay. It's not about, okay, no, we should not memorize, okay, what is that Stressen's matrix multiplication T of n 7 times T of n by 2 plus 18 n by 2 whole square. It's not that way. Okay.
Sir, in this example, the
Okay.
number of multiplications we have reduced from 8 to 7.
Yes, sir.
So thereby we could see the order of growth means it is improvement in the order of growth.
I see.
Reduced. So is there any limitation, sir, to go further down? Suppose instead of 7, 4, instead of 7, can we come down to 4 also? So that
That is also possible, but no one has done that.
okay.
The research means like that only people do know, sir. Now, those who are doing related to this domain, first they'll see what are the existing algorithms. That is called literature, no? Literature. Okay, first they start with n-cubic time algorithm. After that, this is the algorithm. First breakthrough, no? After that, Cooper-Smith-Winograd algorithm is there. That is n power 2.3 something. Okay, dot exact decimal point I don't remember. So now, if someone could reduce it from 7 to 5, log 5 base 2, how much? Log 5 base 2.
2.1.
2. Yes, exactly. I too don't know. Log 5 base 2. So if it is better means, then that's correct. No. If someone does like this with 4, then it will be very much better. Then what is the answer we get? N squared log n. No one has done it. Correct, no? Like this researchers, no, they work on this. Maybe at some point of time they get better improvements. Okay.
Yeah.
Which algorithm you said, sir, the faster matrix multiplication?
Cooper-Smith-Winograd, no? Cooper-Smith-Winograd.
Sir, can you please mention somewhere in the slides so later we can refer it?
Spelling, see, I doubt spelling is PP. Cooper-Smith, Winograd. Smith, Winograd. N power 2 point something. I don't remember exactly the points of it. It is very much better than this algorithm. Okay. Now we'll see some problem based.
So in this case, sir, the memory requirements are here because we are storing so many intermediate values, no, like S1, S2.
Yeah, yes.
Memory complexity, do we see any increase in this, sir?
Because here it is not constant, no?
Yeah.
Unlike other algorithms, it's not constant. Definitely, we need other arrays. So it will be some, we can say it is theta of n squared. Is that correct?
Yeah.
Is that correct?
Yes, sir.
That again, it depends on the implementation, like merge sort, no. Merge sort, so there are in place versions, not in place versions. Okay, that is sorting algorithm. That's why I'm saying in place and not in place. But other algorithms, we don't say in place, not in place, no?
Okay.
Okay, we will see one simple problem based on this. Please, all of you read this statement. Have you understood the problem? See, X be a computational problem. Let A and B two different algorithms to solve X. A also solves X, even B also solves X. Okay. Algorithm A runs in theta of n squared time. It runs in theta of n squared time. Algorithm B solves problems of size n by dividing them into S subproblems. So input size is n. It divides them into subproblems, each of size n by 9. Size n by 9, n by 9, n by 9. Correct? Like this, how many subproblems it is dividing? And this one, S subproblems, S subproblems. And combining the solutions, in theta of, so after that we will get solution 1 like this is solution S. We are combining how much it takes? Combining part it takes order of, okay, theta of n power 1.5. What else is given? Also assume that time required to divide the problem of size n into S subproblems of size n by 9 is big O of n log n. In order to divide this, what is the amount of work we are doing? Big O of n log n. Okay. Is that, now you tell me, what is the recurrence relation for running time of algorithm B? If n is input size, algorithm B.
S
What is T of n equal to S times
T of n by 9
T of n by 9 plus
plus big O of n log n plus big O of plus theta of n power 1.5.
Is that correct? Is that correct?
Yes, sir.
This is divide. Sorry, this is conquer. This is divide. This is combine. Is that okay? Okay. Now algorithm B is like this. So this divide and combine. It is n log n. It is theta of n power 1.5. Out of these two, which is more?
N power 1.5.
So big O of n log n we can simply ignore, no?
Yes, sir.
Can be written S times T of n by 9 plus theta of n power 1.5. Is that okay? Now the question is, if algorithm B to be asymptotically more efficient than algorithm A, algorithm A, what is the time? Algorithm A, they have given somewhere. Okay, A is n squared time. It is more, B is more efficient than A means what? B more efficient than A. B is more efficient than A. That means what is the time for B?
Order of growth.
Definitely order of growth of B and order of growth of A. This is n square. That means it should be strictly less than n square, no? Is that correct? Is that correct? Is that is up to this? Is there any doubt?
Yes, sir. Yes, sir.
Okay. Now finally order of growth of B we should get as smaller than n square. Now if S equal to 1, if S equals to 1, then what is reconciliation? T of n by 9 plus theta of n power 1.5. Which case is applicable? Which case is applicable?
Case 3.
So finally T of n is theta of n power 1.5. Is it better? Is it better?
Yes, sir.
Yes. If S equal to 2, T of n is 2 times T of n by 9 plus theta of n power 1.5. Which case? Same
only,
case, same
same.
answer. Even if it s equal to 8, same thing, no? Is that okay? Is that okay? Even s equal to 9, if s equal to 9, if s equal to 9, which case?
Case 3 only, sir.
If s equal to 9, also case 3. So that's why they have they asked only for maximum number of subproblems. Minimum means what we could have easily said, no? Only one subproblem or without even solving subproblems. But that becomes okay, no? One subproblem. Number of subproblems is only one, we can say. But that's why they are asking for maximum number of subproblems. That means what? What is the maximum value we need to choose for S so that still our algorithm B is better than algorithm A. Algorithm A. Is that okay? Is that okay? Are you getting?
Yes, sir.
Okay. So now that means even if we get n power 1.9 something like this, whether our algorithm B is better or not? N power 1.99, is it better or not?
Yes, sir.
So now finally we ensure that overall whatever answer we get, that is better than n square. That means it can be even more than n power 1.5 or not. That means it can be even more than n power 1.5 or not. It can be more than n power 1.5 or not.
Yes, sir. Till
It can be more, no? It can be even more than n power 1.5. Only it should be less than n square. Only that much we want. That much we want. Now you tell me which case which case of master theorem is applicable if overall answer can be even more than n power 1.5. That means every time what is that we compare f of n and n power log a base we know. F of n is n power 1.5. What is n power log a base p? N power log s base 9. Is that okay? Is that okay? Now what is that we want now? What is that we want? What is that we want?
value of A.
It can be even n power log s base 9. It can be even more than this. That is no problem. That means what? Which case of master theorem is applicable? Which case of master theorem is applicable in this case?
Case 1, sir.
Case 1. By case 1, what is the answer? What is T of n? Theta of n power log s base 9. Is that correct? Is that correct? But what is that we want? What is that we want?
The
N
value of
power
S.
log s base 9, it should be less than n square. Is that okay? Now bases are same. We can compare the powers, no? That means what? Which implies log s base 9 should be less than 2. Is that okay? That implies s should be less than 9 square. Is that okay? S should be less than 9 square. 9
Yes,
square
sir.
strictly less than. Okay, no, number of subproblems integer we consider, no? So it is less than 81 means what is S value? If S is integer, maximum value for S is 80. So that means what is the maximum number of subproblems we need to solve so that still algorithm B is better than A? 80. So that means now you can put, okay, here T of n is 80 times T of n by 9 plus theta of n power 1.5. Which case of master theorem is applicable here? Which case of master theorem is applicable here?
Case 1, sir.
case 1. Why? Because it is definitely more than n power 1.5. No, log 80 base 9. 81 base 9 is 2. 80 base 9 may be 1.9 something. Okay, 1.9 something. That's why case 1. So answer is definitely less than n square. Okay. So what is maximum value of S? 80. Maximum value of S is 80. All these things only we simply should know the concept. What is divide, what is conquer, what is combine, what does order of growth mean, how to apply master theorem. That's all. It is not memory based, but only we need to understand the concept. That's okay. I think that this, can you please give me answer whether this is true or false?
The answer is already given here.
That means true or false? That's what I said. Is it true or false? Ditto, similar to previous problem. We have two algorithms to solve X. A runs in again as usual theta of n square time. What is the amount of time B takes? That we need to calculate by dividing into S subproblems. It divides into S subproblems. Each of size n by 8.
So it is true.
Sir, true. Again, one more
Yeah.
time, sir, please check. Okay. Yes, each of size n by 8. And combining the
Yeah.
solutions in this
Sir,
is,
I think 63, sir.
thank you, brother. 63 is correct. It is strictly less than 64, no, sir.
Yes, less than 0.5.
That's all. Okay, solution yes. Solution yes. Combining this, it takes how much time? Combining the solutions, it takes theta of n time. Theta of n time. Time required is dividing step. They have clearly given it is constant order of 1 time. Again, as usual, B should be better than order of growth of B should be less than. Better means order of growth should be less now. Okay, like this. What is reconciliation here? S times T of n by 8 plus order of 1 plus theta of n. Is this okay? It is same as S times T of n by 8 plus theta of n. Now, if S is 1, is it better than A? If S is n, is it better than A? Yes, no. If S is n, T of n is T of n by 8 plus theta of n. Which case of master theorem? Case 3. T of n is theta of n. That means very much better than theta of n square time algorithm. If S equal to 8, if S equal to 8, T of n is 8 into T of n by 8 plus theta of n. Which case? Case 2. T of n is n log n. Is that okay? Is it clear? So that means now we can assume, because n log n is very much smaller than n square. No, that means our algorithm running time, it can go even up to 1.9, something like this. So that means we can assume that S is definitely greater than 8. Is that correct? S is greater than 8. Why? Because we are looking for maximum value of S. So therefore, what is T of n? S, which is greater than 8, T of n by 8 plus theta of n. Now, which case of master theorem? Case 1, it will be theta of n power log S base 8, but it should be less than theta of n squared. That means log S base 8 should be less than n squared, which implies S should be less than 8 squared, that is 64. So therefore, S should be only 63. Is that okay? Is that okay? If it is 64, both have same order of growth. So that means algorithm A is not better, no, asymptotically. If S equals 64, both will have same order of growth. Next. Now, next we'll discuss one more problem, which is of divide and conquer type, large integer multiplication. So if we are given two integers in decimal, say x equal to 1, 2, 3, 4, and y equals to 7, 8, 9. In order to multiply and find the product xy, how many single digit multiplications are required? How many single digit multiplications are required in order to find xy?
12.
So by classical method, so what is that we do? Each digit in y will multiply with each digit in x, then we take summation, no? So that means classical method, 4 into 3, that is 12 multiplications. 12 multiplications. In general, if x has n digits, I am considering both x and y in decimal only. Decimal. X has n digits and y has m digits. Y has m digits. In order to find xy, how many single digit multiplications are required? To find xy, m into n single digit multiplications. This single digit multiplication, hereafter I call it as scalar multiplication. That means single digit multiplication. Scalar multiplication. Okay, m into n scalar multiplications are required. If both x and y both are n digit integers, then how many multiplications are required to find xy? How many multiplications are required? Both x and y are n digit integers.
N square.
N
N
square.
square. N square scalar multiplications. Now the question is it possible to multiply two n digit integers in less than n square time? Is it possible to do n digit integers in less than n square time? Goal. What is our goal? Little o of n square time algorithm. That means strictly lower than order of growth is strictly lower than n square. Okay, little o of n square time algorithm. Okay. How to do that? Now we learned one algorithm design technique called divide and conquer. So is it possible to apply divide and conquer method and get better running time for this algorithm or for this problem or not, to solve this problem or not? Say x has, if x is 6342 and y is 4513, something like this, then is it possible to write x as 63 into 10 square plus 42? Similarly, y as 45 into 10 square plus 13. Is that correct? Is that correct?
Yes, sir. It is correct.
So in general, if x has n digits, total n digits, assume that n is of the form 2 power k, so that always, if I divide, no, it with reminder 0, it divides. And this is left n by 2 digits. Left n by 2 digits. This is right n by 2 digits. This. Now, if we are given 1, 2, 3, 4, 5, 6, 7, 8, can we write it as 1, 2, 3, 4 into 10 power 4 plus 5, 6, 7, 8? Is that correct?
Yes, sir.
Okay. In general, if we are given a number which contains n digits, then is it possible to write x as this left part I call it as XL, right part we call it as XR. This is left part, this is right part. Here what is XL? XL is 1, 2, 3, 4, XR is 5, 6, 7, 8. Okay, XL, XR. Now can we say that X is same as XL into 10 power n by 2 plus XR? Is that correct? Is that
Yes,
correct?
sir.
Similarly, Y also can be written as YL into 10 power n by 2 plus YR. What is XL? Leftmost n by 2 digits. What is XR? Rightmost n by 2 digits. Now we are assuming that it has always n equal to 2 power k number of digits, so that both sides will get equal number of digits. Is that correct? Now what is x into y according to, now what is x into y? Okay, let us write in next slide. What is x into y now? What is x
XL into YL into 10 raised to n by 2.
plus XR into YL into 10 raised to n by 2 plus YR. Is that okay? So now if we multiply, can we say that XL YL XL YR n plus XL YR plus XR YL into 10 power n by 2 plus XR YR. Is that correct?
Yes, sir.
So now in order to multiply, X has n digits, X and Y both n digits each. N digits each. So to find the product, whatever is time is required, let us call it as T of n. T of n. Now, if we are calculating the product based on equation 1, how many subproblems we are solving here? How many subproblems we are solving here? Is it one subproblem or not?
Total 4 subproblems.
N by 2 digit, no? Here it is n by 2 digit multiplication. This one is n by 2 digit multiplication. This is also n by 2 digit multiplication. This is also n by 2 digit multiplication. Is that okay? Now, how many subproblems we are solving? 4 subproblems. What is the time for each of the subproblems? T of n by 2, can you say? Is that okay? Is that okay? Now, what after that we need to multiply with the 10 power n. Can you consider it as new multiplication? Not necessary. 10 power n multiplication is easy in decimal. Why? Because simply if I shift the elements, no, automatically we'll get 10 power 1, 10 square, 10 cube like that, no? Are you getting?
Yes,
12,
sir.
12, 2, 1, 0 I'll put. This is nothing but 12 into 10 power 1, no? If I shift to 2 times here and 2 zeros here, this is nothing but 12 into 10 square, no? Means in order to multiply with the 10 power n, we need not do any actual multiplication there. Only shifting operation we perform. Similarly, here also it is shifting operation. But how many times we need to do shifting here? N times. N times shift. Here n by 2 times. Shifting. After that, again we need to add, no. To add 2 n-digit integers, maximum how many additions we perform? To add 2 n-digit integers, maximum?
N.
N. Whatever integers we get here, definitely they are not more than n-digit integers, no? Maximum n plus 1 digit integers we get. Is that okay? Is that correct? Whatever multiplication here we get, whatever we get here. Sorry. Okay. Whatever we get here, it is maximum n plus 1 digit. Is that okay? Two 2-digit numbers, if I multiply, maximum we'll get a 3-digit number. No, that's all. No, maximum 99 into 99. That's all. No? Is it 3-digit number or more 4-digit number? Similarly, 2 3-digit numbers, if we multiply, maximum we'll get 4-digit number 999. That is 4-digit number only, no, not 5-digit. Is that correct? Whatever I said?
Yes, sir.
Okay. So it is easily we can add these results in n time. So combining only takes n time. Combining only takes n time. Okay. Dividing also easily we can do in constant time. So now what is the total time this algorithm takes? T of n can be written as 4 times T of n by 2. Plus this is theta of n, this is also theta of n, this is again adding also theta of n, all those things we can simply write theta of n. If n equal to 1, we can write it as simply 1 constant or 1. This is the reconciliation we get. Which case of master theorem? Which case of master theorem?
First case.
T of n is
N square.
n square. Why should we do this? Without doing classical method also we get the same answer, no? Classical method also we get the same answer. Then how to improve this? Instead of 4, if someone gives 3, whether automatically improved or not? Instead of 4 here, someone gets only 3. They are able to solve it with 3 subproblems of size n by 2. Automatically it is improved. That's what Karatsuba has done. That means what is the reconciliation in Karatsuba's large integer multiplication? Instead of 4, they'll have it has 3. This is Karatsuba's. That we will discuss in next class. I stop here.